Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the Gibbs phase rule. So in the earlier sessions we have discussed about how to draw the phase diagram and what are the different phases are available in the phase diagram. Now this Gibbs phase rule helps us to identify how many number of phases are there, what are the compositions of the elements or alloys which you are taking in the phase diagram, and also how to draw the phase diagram. So all these can be available with the help of this Gibbs phase rule. So in order to construct any phase diagram or understand the conditions of equilibrium, the thermodynamics laws are very useful for us to draw the Gibbs phase rule or phase diagrams. So what does this Gibbs phase rule infers for us means it will provide the information of how many phases are present in the phase diagram, as well as what are the variables in the phase diagram and how many degrees of freedom of these variables are present in the phase diagram. So depending upon these variables, we can easily draw the phase diagram of any given alloy or any given composition with respect to temperature. So in construction of any phase diagram, this Gibbs phase rule is very useful and important in drawing the phase diagrams of any type of given alloy. Now, the rule represents the criteria for the number of phases that will coexist within the system at equilibrium. So this Gibbs phase rule describes for us, and it will give the number of phases present in the phase diagram at the equilibrium conditions. And the equation for the Gibbs rule is given by P plus F is equal to C plus M. So this is the Gibbs phase rule in which we have the equation as P plus F is equal to C plus M. So we have to know that this Gibbs rule is useful for us to identify how many number of phases are present in the phase diagram. That is very important when you start drawing the phase diagram. Now we'll see what is P, what is F, what is C and what is N in the coming slides. Now in this Gibbs phase rule, as you know, P plus F is equal to C plus N. In this, the first term, the P represents for the number of phases present. So in order to identify in any given problem how many number of phases are present, then we can use this Gibbs phase rule, and it is very easy for us to identify how many number of phases are present in the given composition. So once if you know the number of phases present in the given phase diagram, it is very easy for us to calculate the composition of any point at particular temperature, whether it is in liquid state or solid state or combination of both liquid and solid states. So this helps us to identify the number of phases, whether it is a single phase or a double phase. So this means, so in this term, the P represents for the number of phases present in the phase diagram. And next, the parameter F is termed as the number of degrees of freedom or the number of externally controlled variables. So here, what are the externally controlled variables? We have like temperature, pressure and the compositions. Now why we are telling this as externally controlled means, so we can control the temperature. Either you can increase the temperature or decrease the temperature. Similarly, the pressure, you can increase or decrease the pressure. Similarly, the composition, you can vary the composition or by increasing or decreasing. So these are all called the variables. So that's why in this equation, P plus F is equal to C plus N, F stands for the number of degrees of freedom or number of externally controlled, what we are controlling the elements or alloying present in the phase diagram. So those are called externally controlled. We can control these elements like temperature, pressure and the compositions. Okay, so these are the three different externally controlled variables in the any given phase diagram. And this must be specified to completely define the state of system. So if once you know the externally controlled variables, then it is very easy for us to identify, or we can express the how the temperature is varying or how the pressure is varying or how the composition is varying in the specified phase diagram. And another way of expressing this F term is a number of these variables that can be changed independently without altering the number of phases. And another way of defining this f, what are the f we are taking, that is the degrees of freedom, rather than the controlled variables, externally controlled variables, we can also define this f as the variables that can change independently. So independently the pressure can vary, independently the temperature can vary, independently the composition can vary without disturbing the phases, without disturbing the phases. So in that way also we can define the f in this Gibbs rule. So two types of definitions we have for the f. First one is the degrees of freedom, or the number of externally controlled variables like temperature, pressure, and composition. So this is one of the definition for the f. And in the same way, these, what are the three variables we have, these can be independently changed without altering the phases in the phase diagram at the equilibrium conditions. So these are the two terms what we have. First one is the P represents for the number of phases. So we can easily identify how many phases are present, either by the 2 or 3 or 4, or how many single phases are present or how many double phases are present in this equilibrium condition, that we can get from this equation. And coming to the f, f stands for the degrees of freedom, that is the components which can be altered like pressure, temperature, and composition externally. So this represents for the f. And coming to the parameters c in the Gibbs rule, what we have here, we have the number of components in the system. So how many components are there? So in the previous sessions we have discussed about the composition of nickel and lead. So that is one of the combination. Next one, we have seen the lead and tin, copper and iron. Like that, we have different compositions. So how many number of compositions are present in the phase diagram can be given by this C here. So in the Gibbs phase rule, the other component what we have is the C. So C represents for the compositions. How many compositions, number of components are there in the phase diagram, that will give us. So depending upon the number of components, we can easily identify what is the composition of each component at each temperature. So that is the useful of the Gibbs phase rule in identifying the number of components or number of phases or number of degrees of freedom which the externally controlled variables. All this can be categorized with the help of these. So if you know all these things, it is very easy for us to draw the any type of phase diagram given any number of phases or given any number of components or given any number of phases. It is very easy for us to draw any type of phase diagram if you know this, if you follow this Gibbs phase. So like the components, what are the components we are taking in the phase diagram in the previous sessions? Two extremities on the horizontal composition axis. So generally we have in the phase diagram two axes, external and internal. So here in x-axis we have the composition, y-axis represents for the temperature. So here this horizontal axis, what are the horizontal axis is there? This is called the composition axis. Composition axis. And the y-axis represents for the temperature. So in this case, what are the components are there? These components can be represented with respect to x-axis. Why? Because these components has to be defined with the composition, percentage weight of composition. So in order to describe the percentage weight of composition, we have to take the horizontal axis as the reference axis. From that horizontal axis, it is very easy for us to identify the percentage weight of each component. So if you take any point like this, if you drop the horizontal at this point, you can get the what is the percentage weight. And if you draw the point along the y-axis, you will get the temperature in degrees centigrade. So this is how you have to identify the components and its composition with respect to the temperature. Now, the example H2O, sugar syrups we have seen in the previous example. Copper and nickel is another example. of the phase diagram. Like this, you have n number of components, If any type of component is given to you, it is very easy for us to draw the phase diagram with n number of components once if you know this Gibbs phase rule. And finally, this n stands for the equation is the number of compositions variables. So what are the variables here? Though we have temperature, pressure and the composition, but the n stands for the number of non-compositional variables. Non-compositional variables are what here? The composition, generally we have the composition, pressure and temperature. So these are the three variables what we have. So in these three variables we have only the non-compositional variables. So these are the temperature and pressure. Except this composition, we can change all these things. So that's why it's called non-compositional variables. Now totally we have 4 variables in the Gibbs phase rule. First, P stands for the number of phases and F stands for the number of degrees of freedom. Those are the terms, those are the components which are externally controlled, like temperature, pressure and the composition. And the C stands for here the components, number of components present, whether it is 2 components, 3 components or 4 components. So how many number of components are present in the phase rule, that can be identified with the help of C. And coming to the last term, here we have the N. So N represents for the non-compositional variables, that is the temperature and pressure. Now in any given problem, if you want to identify the number of phases, so in any question they'll ask how many number of phases are present in so and so example. So what you can tell, by using this Gibbs phase rule, it is very easy for us to identify how many number of phases are present in that phase rule. And in another question, if they're asking to identify how many number of variables are there, it is very easy for us. Once if you know the phases, the C and N value, it is very easy for us to find out what is F value. Similarly, in another case, if you want to find out the components, number of components, so we can use the same Gibbs rule and identify the number of components. So like that, if you follow the Gibbs phase rule, it is very easy for us to identify the number of phases or the number of components which are variables and the number of components which are non-variables, and also how many degrees of freedom are there. So all these things can be identified or calculated with the help of this Gibbs phase rule. So that's why if you want to draw the any type of phase diagram with any type of composition, so it is very useful to know the Gibbs phase rule, and after knowing this Gibbs phase rule, it is very easy for us to draw any type of phase diagram. Now, if you want to still get clarity in this, we will take some example to demonstrate how this Gibbs phase rule is applying on the binary temperature composition phase diagram. So it will be more clear if you once go through this example and identify what are the steps which are to be followed in order to demonstrate the same Gibbs phase rule for the binary Eutectic system. So in this case, what we're taking here, the Gibbs phase rule we are applying on the binary temperature composition phase diagram. So we'll take copper, silver as an example to demonstrate this Gibbs phase rule. So now what is happening here? Because the pressure is constant and the parameter N is one temperature, is the only non-compositional variable. So what is happening here? Since the pressure is constant, so what is the other variable here? We have only the temperature. Okay, so that is the only non-compositional variable here we are having. So in this equation, generally we have the Gibbs phase rule as P plus F is equal to C plus N. So this is our general Gibbs phase rule. So in this case, what we are doing here, so P is the number of phases, of course F is the degrees of freedom, which is the components that are externally controlled. Okay, C is the number of components present, and N is the number of non-variables. Now in this case, since we are taking copper and silver as an example to illustrate or to demonstrate this Gibbs phase rule, So what is happening here? Pressure is being constant in this case. So what is the non-compositional? Only the non-compositional variable here I am having the n. So that is the one. So that's why only one term is there. Suppose if both temperature and pressure are there, then you have to replace this one with 2. But since only one component is non-variable in this case, that's why we are writing this n as 1 here. So we are writing n as 1 in this case, since we have only one non-variable component. Now furthermore, the number of components here, how many number of components we are taking here? Copper and silver. So here 2 components we are taking. So that's why what we have to do next, C. C stands for the components in the Gibbs phase rule. Now since we are taking copper and silver as the 2 components in this case, so you have to replace this C with 2. That's why we are writing, since 2 components we have, copper and silver, so we are taking it as 2. So finally what we are getting, P plus F is equal to 2 plus 1. C is 2 and N is equal to 1. Okay, you have to differentiate between what is C and what is F. Always F stands for the components that are externally controlled. So what are those components which are being externally controlled? Temperature, pressure and the composition. So these 3 are the externally controlled variables in the phase diagram. And coming to the components means number of components present in the phase diagram. So how many components, whether it's copper, silver or nickel, brass, iron, carbon. So you have different compositions we have. So you have to identify how many components are present. So in this example, we have taken only 2 components. That's why the value of C is 2. And coming to the N, N represents for the non-variable components. So what are those non-variable components? We have temperature and pressure. Since in this case, pressure is constant, so the remaining non-variable component is what? Temperature. So only one term we have. So that's why we are taking N as 1. So totally P plus F is equal to 2 plus 1, that is 3. From this case, we can rewrite this equation as F is equal to 3 minus P. We are just rewriting the same equation. F, in terms of F, we are getting as 3 minus P. So now, for the same example, we are considering the case of a single phase. So we are considering it as a single phase. So that's why what we are trying to do, what are the single phases? Either liquid or it should be solid. So in the copper and silver phase diagram, what we have discussed in the previous classes, we have totally alpha, beta and liquid phases. So 3 single phases we have. So that's why in this case what we are taking here, considering the case of a single phase on the phase diagram, example alpha, beta and liquid regions. So these are all the single phases. And because only one phase is present, so all the things we have only single, there is no combination of either liquid or solid. So wherever you see, we have only a single phases, either it can be alpha or beta or liquid. That's why we are taking it as P as 1. So in the previous equation we have written F is equal to 3 minus P. Now the P value, since it is a single phase, P we are taking it as 1. So this is 1. So totally we are getting F is equal to 2. So from this Gibbs rule, we are getting F is equal to 2. So what this infer? What is F is equal to infer means? This means that to completely describe the characteristic of any type of alloy, that exists within a single phase, the 3 phases field, what is happening? We must have 2 parameters. This is very important. Okay. So in order to describe the characteristics of any type of alloy within the 3 phases, what are the 3 phases here? I am having alpha, beta and liquid region. So in order to describe those, in order to identify those characteristics, we need to have 2 parameters. So what are the 2 parameters? F is equal to 2. Since F is equal to 2, so we need to have at least 2 parameters are required to describe the characteristics of that phase diagram with any given type of alloying element. So this is what we are getting the information from that F is equal to 2. So minimum 2 parameters are required. Either it should be temperature, pressure, or temperature composition or pressure composition. Any. Okay. any two parameters are required to describe the characteristics of the given phase diagram with respect to these alpha, beta and liquid phases. And these composition, what are those two parameters here? We have temperature and the compositions. So with respect to these two only, we can easily describe those characteristics. So generally, these are the two things we have: temperature, and here is the composition. So once you know these two parameters, suppose some x point is there. If I want to describe the characteristics, how I'll describe the characteristics? This x is lying in which phase? Whether it is lying in liquid phase or solid phase or combination of both, I have to describe this x point. So how can you describe? If I know these two parameters, if I know the temperature as well as the composition, then only I can describe the characteristics of that x point with respect to these two axes, these two compositions. Similarly, if you want to know the composition, I have to describe the composition of this x point. How I will do? I have to again drop the horizontal vertical line from that x point to the horizontal axis in order to find out what is the weight percentage. So again, I am describing that x point with respect to weight percentage. So with respect to percentage weight, I'll describe this x point. Similarly, if I want to describe that x point with respect to temperature, what I have to do? I have to draw again a horizontal line on the vertical axis. So then I'll get what is the degrees centigrade. So like that, if any point has to be described in a single phase, at least two components are to be there to describe the characteristics of that given point. So this f is equal to 2 infers that the 2 is nothing but two components are required to describe the characteristics of any given component. So that is what for a single phase. Again specifying it is for a single phase. Single phase, we are getting this f is equal to 2. Now the same condition if you take for the two phases, for the two phase system, what happens here? Two phase means, for example, alpha plus beta combinations. In the previous case, we have seen only alpha or beta or liquid. That is for single phases. Now, if you go with a double phase or a two phase system, it is a combination of both alpha plus L, beta plus L, or alpha plus beta. So here you are having two phases here. So the same f is equal to 3 minus p. In this case, phase is representing p. In the previous case, it is a single phase. That's why we are taking p as 1. Now, since it is two phase system we are considering here, we are taking p as 2. So what we are getting here, f is equal to 1. F is equal to 1 we are getting for a double phase system. For a single phase, we are getting f is equal to 2. Now, since this example we are taking f, it is a double phase, so f we are getting as a 1 value. So again, what it is inferring here means it is necessary to specify either temperature or composition of a one phase to completely define the system. So in order to define the double phase system, you need to know any one parameter, either temperature or composition in this phase. So this f is equal to 1 infers that to specify the characteristics of any given component, either temperature or the compositions has to be known to describe those characteristics of the given phases for the double phase system or a two phase system. When coming to the single phase, minimum 2 should be required. For a single phase, minimum 2, that is composition as well as the temperature. But coming to a double phase, either composition or temperature should be known to describe the characteristics of any given component. So like this, in order to describe the complete phase diagram, if you want to know how many phases are there, how many components are there, how many components are required to describe, or how many components which are being externally controlled, or what is the number of components present in the phase diagram. So all these can be calculated or identified with the help of this Gibbs phase rule. That's why Gibbs phase rule is very, very important for us to draw or to identify or to calculate or to characteristic the given component. Okay, so all these are been helpful with the help of this Gibbs phase rule. And coming to the next important phase diagram, we have the iron carbide diagram. So this is very important phase diagram what we are seeing. So here, how this iron is changing to a carbide. So with variation of temperature, with variation of compositions, how it is being varied with different phases, we will see in this phase diagram. So here, again, we have x-axis as the composition axis. We can see in the x-axis, and y-axis represents for the temperature. So while drawing any phase diagram, this rule we have to follow. X-axis represents for the composition, and y-axis represents for the temperature. So that we need to follow. And depending upon the components, we have to give the percentage, weight percentage, and at any point, if you see, the total should be 100. So this we have discussed in the previous classes also. At any point, if you see, the total composition of these two components should be equal at any point. At any point, if you see, throughout the horizontal axis, at any point, if you see, the total composition should be 100. So that's why if the iron is starting at this point 0, the carbide should be 100. Similarly, at the extreme right side, if the carbide is 100%, iron should be 0. So that's what this iron carbide or any phase diagram has to draw. Again, coming to the y-axis, that is the vertical axis, we represent with the temperature in degree centigrade. Now, this we are seeing a portion only. We are not seeing completely. If you closely observe this phase diagram, we are stopping at this 6.70 weight percentage only. Generally, we have to go to 100%. Why we are not going up to 100% means at 6.70 weight percentage of carbon, we are getting this carbide. That means this iron, whatever the iron is there, it starts from 0, and after reaching that 6.70 weight percentage, we are getting the exact carbide. So that's why we are stopping. So we are having some partial phase diagram only. We are not getting a complete. If you go to 100%, we are getting graphite. So that is another phase. But since we are concentrating only on iron carbide, okay, from iron to carbide, so this phase diagram is restricted. It is a portion up to 6.70% only. 6.70. So this is not up to 100%. So you have to see this figure clearly. And at this point, so we are getting a cementite. That is the carbide. So that's why we are stopping at that 6.70 weight percentage of carbide. Now, pure iron, in this phase diagram, you see pure iron upon heating experiences two changes in the crystal structure. So what is happening here? So this is the difference in any type of composition what we have. Any pure iron, if you heat, what happens? It is experiencing two changes in the crystal structure. That means, suppose if it is in FCC, once you heat, it changes to BCC. Again, it is converting from BCC to FCC again. So it is changing during the heating process into two crystal phases. So any pure iron, when you heat, what is happening? It is experiencing two changes in the crystal structure. FCC to BCC, again BCC to FCC. It is coming back. So that is the two changes in the crystal structure. So at room temperature, the stable form is called as a ferrite. That means at this point, what are the ferrite you're seeing? So what are the iron is there at room temperature? The stable form of that iron is called as a ferrite or iron. And it is having, what is the structure? We are having a BCC structure. So initially at room temperature, whatever the iron or the ferrite we have, it is having a BCC phase structure or BCC crystal structure. Now ferrite experience polymorphous transformation. Polymorphous means occurring in several different forms. That means it is changing. Once you start heating the system, once you start heating the iron or the ferrite, what is happening? Slowly it is changing polymorphic crystal structure. It is transforming from one phase to other phase. That's it. At initial state, it is having BCC. So after heating, what is happening? It is converting to FCC. So after transformation, what is happening? It is converting to austenite. That means from iron, that is from ferrite to, it is converting to austenite. So from BCC ferrite to austenite FCC. At what temperature? At 912 degrees centigrade. So at room temperature, we have a ferrite, that is the iron, which is having BCC. Now, since it is heating, so after reaching 912 degrees centigrade, this ferrite is converting to austenite, which is having FCC phase structure. So you can see here, at room temperature, we have a ferrite. So slowly, if we increase the temperature, this is increasing in temperature. So at this point, 912 degrees centigrade, this ferrite, alpha ferrite, is converting to gamma austenite. That is, it is changing its phase. Okay, it is changing its crystal structure from BCC to FCC. At room temperature, it is ferrite. Now, after heating and after reaching that 912 degree mark, it is converting from ferrite to austenite with BCC, FCC crystal structure. Now, this austenite, after converting from that ferrite to austenite, what is happening? The austenite is existing up to 1394 degrees centigrade. That is, at this point, till this point, you have that FCC with that FCC structure. Okay, austenite which is having FCC. So, after that, what is happening? Again, it is reversing to BCC phase, which is known as a delta ferrite. Again, ferrite, austenite, and delta ferrite. What is happening here? From BCC, it is converted to FCC, and from FCC again to PCC. That's what the polymorphous. It is transforming its crystal structure from one to another. So, what are the pure iron we have? Once you heat this pure iron, so what is happening? This pure iron is changing its crystal structure. So, at room temperature, initially, it is having ferrite with BCC crystal structure. So, slowly upon heating, after reaching the 912 degrees centigrade mark, it is converting into austenite, and this austenite will remain same up to 1394 degrees centigrade with FCC. Now, after reaching that point and beyond that point, after crossing the 1394 degrees centigrade, what is happening? Again, this austenite is reversing. It is reversing back to again the ferrite, which is having BCC crystal structure. That's why this is transforming into two different crystal structures from BCC to FCC again to BCC, like that. Okay, so that is called, after falling from the 1394, it is called as a delta ferrite. So where you are getting? We are getting at 1538 degrees centigrade at this point. So here we are getting this delta ferrite, which melts at 1538. So at 1538 degrees centigrade, we are getting the melting point of iron. So up to that, you are having the solid nature. So after that only, we are getting the melting point. So all these changes are apparent along the left vertical axis. So all these changes, what are the changes? We are seeing that alpha ferrite to gamma austenite and delta ferrite again. All this we can see with respect to these vertical axis with respect to the temperature. So this is very, very important. So depending upon these only, we are trying to draw the phase diagram for this iron carbide diagram. So at the initial stage, at the room temperature, we have the ferrite. There is a BCC structure of that iron. And after reaching to 912 degrees centigrade, whatever the ferrite is there, it is converting to austenite. And it is remaining up to 1394 degrees centigrade. After that, it is again transforming to delta ferrite with BCC. So that is what the transformations polymorphous of this iron. And after reaching this 1538, it starts melting. So in the previous classes also we have discussed, in order to identify what is the melting point of any given type of material, it is very easy for us. with respect to the phase diagram. Once you draw the phase diagram, once you know the phase diagram, it is very easy for us to identify what is the melting point of any given material. So in this case, at 1538 degrees centigrade, we are getting the melting point of that iron. So this is the exact picture of the iron carbide diagram. So this is the composition what we are having, and this is the temperature. Now it is starting from the normal temperature. There is room temperature. So we are getting here inside as the alpha ferrite, and slowly if you raise the temperature, it is reaching 912 degrees centigrade. Now it is converting to austenite, that is the gamma austenite, and slowly if you raise the temperature, so all these are is in the solid form. Okay, we are not getting any liquid thing. So slowly you are heating again. It is reaching to 1538 to get the delta ferrite, and from here you are getting the liquid. That's why it is liquid. So this is the liquid melting point of that iron. That's why we are getting a liquid L here. Okay, so this is how it is being transforming from one crystal structure to another crystal structure. Now, if you see the composition axis, that is the x-axis, the figure is extending up to only 6.70 weight percentage of carbon. Why means, so we are concentrating only the conversion of iron to carbide. So it is converting from iron to carbide at 6.70 weight percentage. So that means we are getting the cementite or the carbide at this junction. So that's why we are stopping. So that's why the figure extends only to 6.70 weight percentage of carbon. At this concentration, intermediate compound iron carbide or cementite is formed. So that's why we are getting the output. The carbide is we are reaching. That's why we are stopping the iron phase diagram at 6.70 weight percentage. So since we are getting this cementite or the carbide is being formed at this point, so that's why we are representing the phase diagram up to this only. So thus the iron carbide system may be divided into two parts. So how we are dividing again this into two parts means by rich composition of iron or rich composition of carbide. So one is rich iron composition. So that is not shown. Why? Because at the extreme right up to 100%, if you go, then you're getting full rich portion of that carbide. And another thing is composition between 6.70 and 8%. So we are getting, if you further go, if you extend this 6.70 to 100%, we are getting graphite. Okay, we are getting graphite. So that is pure graphite. So pure iron at this point we are having 100%, and pure graphite we are getting at this point. Okay, so in between we are getting carbide. That's why we are stopping at this point. At this point, 6.708% we are getting carbide. That's why we are stopping. If you go further, if you reach the 100% of carbide, so what we are getting there, we are getting a pure graphite. So at the extreme left, we are having pure iron, and similarly at the extreme right side, we are getting pure graphite. So these are the two. In intermediate, in between, we are forming cementite or iron carbide. So any two names, single name, either iron carbide or cementite Fe3C. This is being formed in between this iron and the graphite. So that's why we are stopping at this point. Now, in practice, all steels and cast irons have carbon content less than 6.70 weight percentage. So in general, what is happening? What are the steels and the cast irons have? They have the carbon content less than 6.70. So below this only, we are getting what are the steels, what are the cast irons are there. The composition weight percentage of carbon is below 6.70%. That's why we are considering the iron carbide diagram at that point only. So further, if you want to know the graphite, we will see in the next sessions. But up to this point only we are considering, and we have to draw up to this phase diagram only till 6.70. So since we are concentrating only on the carbide, so this would be more appropriate labeled Fe3 phase diagram. That's why it is being labeled Fe3. That means iron is converting to carbide or cementite. So if it is again graphite, you have to extend up to 100%. Since we are concentrating only iron to carbide, So we are designating this name as Fe3 phase diagram. So since we are considering up to that point only. So that's why for the convenience, the composition stress will be expressed as weight percentage rather than weight percentage of Fe3, that is carbide, corresponding to Fe3 100%. So if it is again 100% weight of carbide if you take, then it is going for graphite. That's why we are concentrating only, we are just writing it as 6.70 weight percentage of carbon. So we are restricting at this point and we are naming it as Fe3 phase diagram for this given. Now, carbon is interstitial impurity in iron and forms a solid solution with each alpha, delta ferrite and with austenite. So what is happening here? So carbon can easily move into the iron or solid. Okay, so it will deform, will change the crystal structure, since the carbon is being slowly, it is going inside of the alpha ferrite or austenite or delta ferrite. Okay, so all these regions, all the single phase regions, whether it is alpha, gamma or delta, all these are single phases which are having a BCC crystal structure. So since the carbon is slowly moving into this, so what is happening here, you can easily observe from this figure. So at this point of 0.022 weight percentage at 727 degrees centigrade, at this point, okay, what is happening here? Only small concentration of carbon is there. Very small concentration of carbon is there. That's why there is some change here at 0.022 weight percentage at 727 degrees centigrade. And what is happening because of this? Because of this low presentation of carbon, very less presentation of carbon. So carbon, it influencing the mechanical properties of the ferrite. So initially the ferrite is being heated at 727 degrees centigrade. So during this temperature, what is happening? Slowly the carbon is, since the carbon is interstitial, slowly it is inserting into that ferrite. So what is happening? It is influencing the mechanical characteristics, mechanical properties of the ferrite. So if you see these iron carbide in this phase, alpha ferrite, so you can identify the small things. So these are all the carbons. Okay, so it has a density of 7.88 grams per centimeter cube. So this is, if you see through the microstructure, you can see this structure of that ferrite, alpha ferrite, below 727 degrees centigrade. So this is the microstructure of that alpha ferrite. And coming to the austenite, that is, if you go further from the ferrite, if you increase the temperature or the alpha phase, what is happening here? When allowed with carbon alone, so always this carbon is being interstitial into the all the phases, whether it is a austenite or a ferrite or the pearlite. Slowly it is being interstitial into that element. So what is happening? It is not stable below 727 degrees centigrade. So up to this point, it is okay. If you further go, that means after crossing this 727, what is happening? It is not stable. It is changing. So what is happening? The maximum solubility is increasing. So from where 7.0022 to 2.14 weight percentage. So it is being increasing. The solubility limit is increasing since the carbon is being adding into that ferrite or austenite. So at 1147, you are getting the maximum value of the solubility. So it is almost 100 times more than the ferrite solubility. So ferrite is having very, very less, 0.02, 0.022 weight percentage. But coming to the austenite, the carbon is being inserted into interstitial characteristics. Because of that, what is happening? The solubility limit is increasing towards the austenite phase. So at this phase, it is being increasing to 2.14 percentage. That is almost 100 times more than the ferrite. And what temperature? At 1147 degrees centigrade, you are getting this point. So the solubility is almost approximately 100 times greater than the maximum. And for the BCC ferrite, since it is converting, okay, from FCC to BCC, at that BCC to FCC conversion of the interstitial, is very, very large. Because of the carbon content is very, very large of the interstitial characteristics, you are getting the sudden increase in the solubility limit at the austenite phase. So this is how you can see. So if you compare the ferrite with the austenite, you're having the solidity in the microstructure of the ferrite when you compare with the austenite. Since the solubility limit is increasing and the carbon content is increasing when you compare with the ferrite with the austenite, okay, this is how you look the solubility, solid structure of the austenite phase. And coming to cementite, if you are going further, so where you are getting cementite, here at this point you are getting cementite at 6.708 percentage. So cementite forms when the solubility limit of the carbon in alpha ferrite is extended below 727 degrees. So below this temperature you are getting this cementite, and where you will get this solid form of your iron when it is transforming into completely cementite at this point. So below only we are getting, below 727 degrees centigrade, we are getting this cementite formation. So Fe3C will also exist within the alpha. So this gamma phase, here also we are having gamma with combination of cementite, and compared to ferrite and austenite, this cementite is having very hard in nature. Why? Because it is completely having the carbon content. So when you compare with the ferrite and austenite, the cementite is having very hard and brittle. So this is having very, very hard, and the strength of these steels are also can be enhanced by the presence of the carbon. So you can enhance the mechanical properties, you can enhance the strength of the iron with respect to the carbon composition. So that's why you're getting a cementite. So when you compare with the perlite or ferrite or austenite with the cementite, it is having more mechanical properties, improved mechanical properties, or enhancing in the mechanical properties. So the two phase regions which are labeled in this can be noted as eutectic system. So what is eutectic means? A liquid when you heat or cool, so when it is transforming to two solids, when a liquid when transforms to two solids, that is gamma plus Fe3C. So this type of reaction is called as a eutectic reaction. So where you're getting here. So this is called a eutectic reaction when the liquid is transforming to two solids, that is called as a eutectic reaction. Similarly, what is eutectoid? What is eutectoid? When a single solid is converting to two solids. So alpha and Fe3C. That means this at this region. So at this region you are getting eutectoid reaction. Once a solid is converting to two solids. So the gamma at 0.76 weight percentage. That means at this point, when it transforms to alpha plus Fe3, that is two solids. So that is called as a eutectoid reaction. Eutectic means liquid is being formed into two solids. That is called eutectic. Eutectoid means one solid is transforming to two solids, that is called as eutectoid. So here you are getting eutectoid, and this is eutectic. And coming to the pertectic reaction, what is happening? Solid plus liquid when it transforms to single solid. So delta plus L. So this gamma plus L or delta plus L. So you can see here. So when it is transforming to a solid. So this reaction, upon heating one solid and liquid, this solid and liquid transforming to another solid. This is called as a pertectic reaction. So where are we getting pertectic reaction? At this point. So complete solid structure we are getting. So total three reactions you have: eutectic, eutectoid, and pertectic reaction. Eutectic means what? You are getting one solid is converting to two solids. That is called eutectic. Eutectoid means one liquid is transforming to two solids, and pertectic means one liquid and one solid converting to one solid. That is called Pertectic reaction. So these are the reactions what we can see in this iron carbide diagram. So with the help of the phase diagram, we are trying to identify how many reactions are there in the iron carbide diagram. So since we are getting the carbide at this point, so we are restricting our phase diagram at 6.70 weight percentage. And these are some of the references where you can identify or we can get what is the Gibbs phase rule, the references, how to know the number of phases present in any given phase diagram, or how to identify the components present in the phase diagram, how to identify the external parameters that can be changed, how to identify the number of components present in the phase diagram, and also if you want to know the iron carbide phase diagram, what are the three reactions involved in this iron carbide, and at what point you are reaching that cementite, that is the carbide, when it is converting from one phase to other phase. And you have to remember that the iron has two changes in the crystal structure. So when you heat the iron, it is being converting from BCC to FCC. Again, it is reverting to BCC. So all this information can be get from these introduction to physical metallurgy, and another book is Essential for Material Science and Material Science and Metallurgy. So these are some of the references where you can get all the information what we are discussing in today's class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.